My name is Brian Verbort. I'm going to be walking you through a demonstration of just some of the capabilities available in the Autodesk Inventor Nest application. This presentation will provide an overview of the functionality and workflows which enable you to nest, optimize material utilizations, create CAM toolpath, and simulate the manufacture of nested components. All this will take place utilizing an existing CAD model from directly within Inventor. So that's where we're going to get started on the demonstration. What you see here is an Inventor assembly design of a desk. This design consists of all of the panels, shelves, keyboard, drawer pulls, and other components that are required to manufacture the entire design. The first step is to initiate the nest creation process. This is done directly from within Inventor in the model browser using a right-click on the top-level assembly. Like all other aspects of the design environment, the creation of the nest is based upon templates. These templates can contain predefined details, things like the unit of measure, material type, and they're easily customized to allow you to kind of quickly predefine common aspects of the designs, which is obviously not only going to help you eliminate repetitive tasks, but it also will help encourage standardization. As you can see, I can choose to create a new nest using one of the templates, or I can choose to merge this nest with a currently open nest document, or even combine this with a nest that's been previously created and saved to disk. Next, the utility scans the assembly, which extracts the information about the components in the design. Information, things like the component name, quantity, materials that might be assigned to those components. During this process, a comparison of the materials in the assembly is made to those that are already defined in the template. And if materials in the design aren't found in the template, you get an opportunity to have the utility create those materials in the nest document for you on the fly. The next part of the process accomplishes a scan of the geometry for each component that it finds in the assembly. It's looking for boundary profiles. These are identified for each one of what we call the source models. These profile shapes are then extracted and added to a list of source files, which can be seen here. You can review and even modify these profiles in the nesting browser panel. We can include additional sources in the nest at this point if we have other components or assemblies for another design, and it makes sense to group them together on this nest with common materials. In the Sources dialog box, you can see the source assembly names listed, as well as the name of the components, the units of measure, the name and the nature of the CAD system that was used to create the component model. In most cases, you'll see the source provider listed here as an Inventor sheet metal environment or Inventor sheet metal part, but other third-party CAD systems are also supported and can be included in the nesting process. You just simply add the model to your assembly in Inventor like you would if it were a native Inventor model, and the nesting environment recognizes those third-party CAD system models. Once completed, the result is a lineup of all the shape profile boundaries that are found. A closer look reveals each profile with a material thickness displayed. Each profile can be assigned a unique color, or a color can be assigned to each profile which shares a common material type. Other helpful display types are also found on this display list. Applying a material-based color scheme will reveal any components which don't have a common material. So notice that the teak used for the keyboard drawer and the bronze drawer pull aren't really displayed here. This is because the parts don't have a common material thickness, which is obviously required for nesting flat sheet materials. The component thickness varies on these parts. They're either going to be purchased items or produced using a different manufacturing method, such as milling or turning. As such, they're going to be automatically excluded from being nested. We can also manually exclude other items from this list if we want to, and that's done by either removing them from the list of sources that are shown here, or we can do it in the following nest dialog box. Next, I'm going to go ahead and create a new nest study to be used for material optimization. This study can be given a unique name, and job quantity can be adjusted if we'd like enough of the components to be created for the building of multiple desks. These values act as multipliers for the component quantity in the nest. In addition, we can adjust the stack size, which would enable us to stack multiple sheets of material on the machine to be machined together for increased efficiencies, obviously decreasing runtime and also helping get high tolerance match sets of components cut at the same time. The nesting study setting also allows us to change the stock corner positioning, and defining minimum and maximum runtime values either extend or limit the length of time that the study is allowed to spend processing when it's looking for alternate position and orientation strategies to achieve the best possible yield percentage. A desired remnant optimization is also a priority we can set so that the remaining material is most usable for other jobs. Once the nesting calculation process is complete, a visualization of this nest is displayed and detailed nest study information is provided. Note the 4x8 material sheet size being used for this nest. If the desired nest efficiency isn't reached, or we'd like to consider other scenarios, modifications can be made to guide and improve this material utilization. One of these methods that we could use would be to change the raw material stock size that's utilized so all the nested components might fit on a single sheet of material. Stock material type and size is referred to as packaging in this utility. The default packaging used for these nests are defined and stored within the template. This is the same template we chose when we started the nesting process. Material package definitions can be added, deleted, or modified in the Process Material Library Manager. In this case, we can see the material packages that were created when the nest was first created. Our packaging includes the detailed information for material type, the thickness, category, density, as well as the material display color that's used in the nest. You can see any default or predefined materials, as well as the packages that we allowed to be created for the components found in the assembly. One of these is the architectural bronze assigned to the desk drawer pull. The other is teak assigned to the pull-out keyboard tray. Any unused packaging can be deleted here if the components aren't intended to be nested. And we can also see the packaging that was created for and assigned to the yoke components in the Inventor design. We can modify the properties from the material, packaging, and the nesting here to help direct the utility to find a more desired material utilization. The material and thickness properties are both populated by the model material and thickness used in the source design. I'm going to adjust the package size for the sheet of stock, and then we can also modify material cost. On the nesting tab, you can set a total rotational deviation as well as a defined angular increment for the utility to use as limiting factors when it's seeking more efficient part orientation during the nest calculations. Allowing these settings is a great idea for nesting materials which aren't sensitive to a grain direction or don't have a specific finish side. However, in our case, we're using oak stock, which obviously has a grain and a preferred finish side. So these settings and the double-sided control, which allows mirroring, are best left disabled in our case. This is also where we can set a desired spacing between the nested parts by providing an item separation distance. Once we've committed these changes and return to the nest, an update's accomplished, which you can see results in a better utilization of the material. We can also accomplish other types of edits to the nest for things like part quantity if spares or additional parts are required for stock. These changes are also reflected in an updated nest. Now that the nest looks good, let's make this geometry available in a way that it can be used to help us generate the CAM toolpath and allow us to simulate the machining process. This will allow us to check for issues and get an idea of how long the machine is going to be running cutting these parts. Selecting a nest enables the data output options. We could export this nest to an AutoCAD DXF file, then utilize it with pretty much any CAM system or directly at the controller depending on your machine. And that's certainly helpful, but it also creates a bit of a broken process which would require us to manually update the toolpath and re-export this DXF file every time a change was made to the nest or a change was made to the source product design itself. Let's instead create a 3D model of the nest and use that for our toolpath creation. I'll be sure to include stock for us to use in the resulting model. When the assembly option is chosen in this dialog, you have some freedom to make some manual adjustments to the nested components if you wanted to. And if you do use that, I suggest that you ground the components once you're done making those manual adjustments to ensure the parts aren't accidentally moved during future editing processes. For our purposes, there's no manual post-processing that we want to do on this, so we'll go ahead and opt to use the part option. Now that that's accomplished, I'll go ahead, select the CAM tab, and go to work doing some basic toolpath setup. I'll select the type of toolpath. In our case, it'll be a 2D profile, cutting profile. And then we're going to choose the type of cutting machine to use and adjust the kerf and any quality options if we desire. Next, I'll select the Geometry tab and choose the contours to cut. Using the Same Plane Faces option automatically is going to select all the contours that lie in the same plane as the one I choose. That's going to keep me from having to do the tedious work of selecting each of these contours independently. On the Linking tab, I can choose to keep the nozzle down, to limit retracts, and to decrease machine cutting time to a bare minimum. I can also define piercing clearance and specific entry positions if you want. Then the toolpath is generated and now enables us to simulate the toolpath. Based upon the simulation results, I can get a duration to use for planning the job and estimating maybe machine runtime. And lastly, we can post this G-code out for the machine to use. And that's it. So from an assembly of parts through the nesting process and into CAM for toolpath, simulation, and then into G-code. I hope that you found this demonstration informative and helpful.